So here were some examples we went through last time. And we went through a number of them. We saw violations of history properties, right? We saw violations of history properties. That's counter 5. We saw violations of invariance. Why is counter 3, which takes an argument n, which indicates the initial value of the counter? What can that violate? It can violate a what? Invariant. It can violate the invariant that what?
Above 0.
Yeah, the value at any one time, you could check that the value of counter is greater than or equal to 0. Right? Because now we can initialize something that's negative. You didn't mean to break it. You introduced counter 3. It seems so innocent. It seems to give flexibility to the world. It's a feature. Well, it's a feature and a bug. I mean, you could break people's code because someone could reasonably deduce from this that it can never be less than 0. Therefore, it's safe to use as an index into an array. Suddenly, you give them something that's negative, and you pass this in as if it's a counter. You broke their code. It's not such a gift to the world. But meanwhile, counter 4 here. This is not about subtypes being, removed for any significant extensions. No, this allows for wonderful subtypes. It's just that it makes sure that they're consistent with the supertype and their promises. So counter 4 here provides some additional functionality. It lets you have a method that doubles the value. Is that okay? Yeah, it's okay. It's perfectly fine. Any value you could get out of counter 4, you could eventually get out of counter by calling increment, 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 right? Or whatever. And double value, if you secretly have a counter 4 and somewhere else in the program it calls double value a couple times on it, and all you think it is a counter, nothing will seem off. As far as you're concerned, it's just a counter, but someone else knows it's a counter 4 and is doubling its value. That's all fine and good, right? But we do need methods to maintain their semantics, their meaning, right? If increment means to increment it by 1 and counter, and it should really be specified very clearly. This is a poor specification, I should say. Increment here shouldn't be doubling the number, because someone could reasonably say, wait a minute, I have this counter, it's supposed to increment, and I call it and it doubles it. That flies in the face of counter. Well, it's because it's secretly a counter 2, and that violates it. This is not a counter, this is a fraud. Just like FredX was a fraud. Remember that? Okay, yeah. Maybe all too well. Okay. So we went through some of these last time. Int bag. We did int bag. So I left you with a puzzle. You left the room, perhaps musing about the puzzle, perhaps determined to forget it. But the question was here, suppose, so we have this int set. And the question is, suppose we have a subclass of it called int bag. And this int bag is just like int set, except that it allows you, if you insert something more than once, it actually keeps track of the number of times you insert it. So if you insert 1 into the set more than once, insert once, insert a second time, it knows that. And so if you end up calling, for example, to remove on it, there'll still be 1 left. The question is that a legitimate subtype of this? That was not the puzzle, because we actually answered that question before you left. Is it, if it's defined that way, so that remove just removes 1 of the elements, is it a legitimate subtype?
No.
Why not?
Because it's not idempotent adding and removing anymore.
Yeah, exactly. So if you add, if with a genuine int set as defined here, you would think if you say insert 1, and you end up doing that more than once, and then remove it once, it should be gone, right? It should no longer be in the set, right? but now we're violating that. Okay, so then the question, and Connor had asked, suppose remove is defined for int bag to remove all of them. All of them. Strips them all out. So we call insert on one, insert on one, insert on one, and we call remove of one, it gets rid of all of them. Is that sort of int bag? If it were defined that way, would it be a legitimate subtype?
You'd have issues with size.
You'd have issues with size. That's exactly it. Ladies and gentlemen, now size would still be increasing. That's not the only thing. I think there might be also arguments you can make about elements, for example, and potentially about subset. But size alone would be reason enough. That someone might, in an algorithm somewhere, be counting on the fact that they're looping over some collection, and every time they see something, they just insert it into set, because they're reasoning that if you insert the same thing more than once, it's just the same effect as inserting it once. It doesn't increase it. And then at the end, they look at the size to figure out how many distinct items were there in this original collection, right? How many distinct integers. And if every time you, in an int bag, you insert something, the size goes up, then that's going to break their algorithm. It's going to break their logic, their reasoning about this. Suddenly, with the property they're counting on, that if you insert one twice, if you insert one once, the size rises. It's not in there already. You insert it, size goes up by 1. You insert it again, already has it. You insert it again, size should not rise. So size is defined as sort of the number of distinct elements in set, because it only contains distinct elements. And if int bag is violating that, then it could break code that is counting on that property, right? Does that make sense? Okay, so it's not enough for remove to remove all of them. Okay. This is on a previous exam, some of these. I don't guarantee it couldn't be on a future exam. I love these in my exam. Oh, these are some of my favorite things to test. Often there's a page or more of these questions, sometimes multiple pages. I feel a hankering to test you on these things. Okay, so course timer. I know you're trying to time when are you going to get out of this course. Okay, course timer. So here we have a timer, and basically when we create it, it starts a timer. Okay, it starts increasing the time since it was first called, first created, right? It's keeping track of the elapsed time since it was first created. And so we could call, and my indentation is screwed up somehow here, but we could call hours, and we'll get the total number of elapsed hours rounded down. So if there's a fractional hour, 4.6 hours, it'll be 4 still. Since the object was created, and minutes is the total elapsed minutes since the object was created. Totally elapsed minutes. So if it was created 3 hours and 10 minutes ago, it would be 190 minutes. Okay. Now there's find timer, which has all the same methods, but it allows you to ask the number of seconds, the total elapsed seconds since the object was created. Is that a behavioral subtype of course timer? Is that a legitimate subtype? Yeah, there's nothing wrong with that. It doesn't break this functionality at all. It doesn't interfere with. Now, mark my reasoning, because this is going to be really helpful for your career as software engineers, but also, yes, for the undergraduates for your final exam. Okay? The first of those is more important in my book. If you fail the final and you have this reasoning ingrained in you and apply it all through your work as a software engineer, I will still hold my head high. Okay? Okay, find timer. I'm not encouraging you to fail that. I know. Is find timer a subtype of course timer? It is. it extends the functionality. It doesn't interfere with this. None of the methods it adds change the functionality of these methods, right? It doesn't change any, in fact, seconds is just an observer here. You're really adding an observer, something that observes the value in a different way, reports it as seconds. And those sorts of methods that just provide an alternative observation on it, I'm not sure I could think of a single example that ever violates the Liskov substitution principle. It's just a convenience, right? It provides you with a convenient way to get some other total for this. It doesn't change the underlying state of the object. It doesn't override anything up here. And so almost always, and maybe it's safe to say always, those epiphenomenal methods, those methods just observed, they're fine. That's perfectly fine. How about modulo timer? So modular timer, in contrast to fine timer, it overrides minutes. How does it override minutes? Well, it figures that that it's more useful for people to, instead of getting a total elapsed minutes, it's going to provide minutes just within the last hour. So, you know, if it occurred 3 hours and 10 minutes ago, it's just going to give you 10 instead of 190. Figures, oh, that's more useful for our clients. Does that adhere to Liskov substitution principle? No. Because if you thought you had a course timer and secretly you had a modulo timer, could you be rudely surprised? Indeed you could. Because this what?
Violates a history.
It violates the history property. It can now go down, right? It could go down. Okay, how about pausable timer? So here, it's just like course timer, but you can pause it and then resume it. Oh, we're adding some great functionality. Oh, people love it. So we can pause it, we can resume it. I don't know that I'd say it will light the world on fire, but it's you know, it's some added functionality. Will that violate the Liskov substitution principle?
Yeah.
Yeah, it violates it. It violates. Why does it violate it? I don't know that it violates a history. Well, okay. So if time t2, it doesn't.
Violates like the basic.
It violates the semantics of what this does, right? Maybe it is I guess I would say it's a history property. I think that's a fair thing to say. It's not a history property in the most trivial sense that you know, T2 is greater than T1, then minutes will always be greater for it, and this violates that. But it violates the meaning of history for this, you know. So pausable timer, that's a violation of the properties of course timer. And I would say it's a history property that it has, because it has to do with its value at two different times. And is it in fact capturing the difference in times between those? You could imagine constructing a case where T2, time T1 and time T2 that's later than it. Maybe T1 here is a construction time. Time T2 occurs 3 hours later. But it's been paused along the way. It violates sort of what value be expected to be returned, right, after those 3 hours. Okay, how about resettable timer? So in this one, maybe like the clock this morning as you woke up for class, you just reset it when you sleep more or something. Here, you can reset and it starts counting up from 0 at a later point. So you can go for 3 hours, say, and then say reset. And then it'll consider that the baseline. It'll consider that as if it was the initial time. It'll be counting from then. Is that observed the Liskov substitution principle? Does that adhere to the Liskov substitution principle if you can reset the timer to start from now instead of from the beginning time when it was created? No, that does not adhere to the Liskov substitution principle. It violates a history property too.
All of these later timers timers act like stopwatches, like you would want timers to exist. And then the first one exists like time, which is not actually that useful when the system provides it.
Yeah, elapsed time from a defined point. Yeah, there's no question that if you had these functionalities in the original thing, in course timer, if you had forethought to build those into the original definition of timer, they would have been nice features to have. But the fact that we have code bases which may be counting on properties as delineated here gives us, without trying explicitly for a pun, it gives us pause, right? Because we could break those code bases that are counting on properties here. And that's just the thing about subtyping. The idea is that there's an open close principle. We should be able to extend the system with subtyping, but not break it. And here, we'd like to be able to extend it with subtypes without worries that it's going to break all this code that's already been created. And that's the problem with these subtypes. But find timer is a perfectly legit subtype. There's actually quite a few subtypes you could create. How about another one? Here's another one. Man, if I didn't say this now, I might put it on the final exam. Still might put it on the final exam. Okay, suppose I were to have a course timer plus. Sorry, I'm not very creative with names. Course timer plus. And that provides minutes and hours, but it also provides sort of, I don't know how to say it, modulo minutes, or minutes within the hour elapsed, or something like that, which gives values similar to what you get from this minutes as attempted by modulo timer. Would that be an okay sort of subclass?
If you don't override minutes.
If you don't override minutes, exactly. Yeah, it's perfectly fine. It's again one of these observer methods. It just provides another convenient way of sort of summarizing the situation, right? That's perfectly legit. So, ladies and gentlemen, you can have lots of subtypes that are perfectly legit. What you don't want subtypes that will capriciously break by introducing them. The code that's been using the supertype can break because people are counting on properties. Now, let me ask this. This gets a little bit more subtle. Let me ask this. Suppose that the people who defined course timer had put in an extra comment here, an extra bit of specification. And they said, course timer, the constructor begins the timer. Please, and they put in a comment, please note that future subtypes or versions of this class might allow for other sort of base times besides the construction time. They might allow for example, resetting the timer, something like that, so that it starts measuring from a later time. Suppose they put in a comment to that effect, be aware, caveat emptor, buyer beware. Other versions of this and subtypes might provide a different point of reference for the time, the initial time from which you're measuring the elapsed time. Suppose they put in a comment to that effect, and then someone introduced a resettable timer. Would that be okay? Would it violate the Liskov substitution principle? No, because someone's been warned that they can't deduce logically that this is always doing it from the initial time, and therefore their code should avoid counting on that fact. So, ladies and gentlemen, it is perfectly within the legitimate sphere of software engineering to put in a specification that says, please note, this is currently an immutable class, but it's not guaranteed to always be so. We will allow for subtypes that are not immutable. If they put that in, it's sort of fair game for anyone who's building code with respect to it that they have to be aware they can't count on immutability, for example. And that may allow them, that may shape them to take extra precautions in their algorithms, like rechecking a property of this instance of the class that they otherwise would assume, well, I check it once, it's always going to have the same value. Yes, Tushita.
So I was thinking about these warnings, and I feel like
Yeah.
wouldn't these warnings just weaken the contract? And
They
if
would.
I look at it, I wouldn't want to use it because I'm not.
Precisely. And this is exactly the you are sailing here between the charybdis of wanting to provide strong guarantees and the Scylla of thereby restricting the subtypes that can be created. Do you know about Scylla and Charybdis?
No.
Yeah. One was a whirlpool, one was a volcano? A rock, a big rock. Yeah, that's what it was. It was a rock against which ships crashed. I think it was in Sicily area off the coast of Italy. And it appears in the Iliad or Odyssey. I hashed them to the same bucket. Sorry. And ships would have to sail between these two dangers and balance these tensions. And really that's a lot of the issue here. We want to provide a contract that's at the same time strong enough people want to be using our classes or interfaces from using them by interfaces, but we also want to provide enough flexibility that people can subtype in useful directions. And really, ladies and gentlemen, I want to mark this point with emphasis. Here we have two consumers of note for our interfaces. One consumer is the people who use instances of our class. People say, oh, I have a course timer, what can I do with it? The second group is the people who want to create subtypes. And they say, this is course timer super type. I want to create a subtype of that. And I would like a bit of extra flexibility with my subtype. And you have to balance between serving those two groups. Both of those are consumers of this interface. And there's something you might give to one in terms of a stronger contract might limit the ability of what others can do as a subtype. So this is a balance we're striking here. But it's better to be aware of that balance and to consciously think about it than to be unaware and impose needless harm on people who are using your contracts. Okay. Other questions about this? Yes, Fahim.
Yeah,
I love these questions.
So you're talking about assigning the specifications on the superclass to determine what kind of modification of the subtypes are permissible to do.
That's right.
You also said previously that the superclass they may be 5 years ago, 10 years ago. You don't know.
That's right.
It's like you want to extend your arsenal, right? You want to.
That's right.
You want to add more weapons, so that's why you make these subtypes. But here, as you've seen from the last two examples there, these are violating the principles, but they can be useful in cases of if you want to do something like that. But
Absolutely.
But you're saying that it violates the course timer because they do not mention in their specification that it can be paused or it can be modified. Right?
Correct, and it's because, let me sharpen that point a little bit, because you're onto something very important here. Yes, your comments are bang on, but the key vulnerability here is that we could have code that is, it was written, assuming the properties of course timer, right? It's written counting on those properties in a tight loop or whatever it's counting on. Here it's a bit of an exaggeration to imagine it, but in reality, when we have real data structures that are rich, we can count on properties, and we do as software engineers. And the real vulnerability, when talking about adding flexibility to our arsenals, that if you have code that counts on a course timer, we can pass into it one of these other subtypes as if it's a course timer. That's the key issue. When we have a a language that supports polymorphism that's automatically allowed. And the question here is, how do we allow for that general language feature of polymorphism to avoid breaking it, needlessly by subtyping, right? And that has some limitation on our freedom for subtyping. And yes, if they didn't anticipate subtypes that would have certain liberties, like they could be paused, or they could be stopped or reset, then basically the people who created course timer didn't give the freedom to subtypers to create a broad set of subtypes in a way that wouldn't be risky to people who are already having course timers. Because we can't control, when we provide a class like course timer, or a contract like course timer, we don't know how people out there in the world are counting on it. And if we didn't have the foresight to head off certain reliance on certain features, now we may be stuck because there's all these customers who are using it in ways that could be violated if we start secretly passing around a subtype as if it's an instance of supertype. Now, within this classroom, within the next week, I think it will be, I will be introducing to you a safer way to do this that will still allow a lot of the benefits that you have in mind with subtypes, but we'll do this in a safer fashion, okay? And that's in the context of subclassing, but the idea that we exploit with subclassing of reuse of implementations through extension, but we're going to see how traits and mix-ins can be used to perform this in a somewhat safer way, okay? Because mix-ins provide a way of reuse of functionality, of implementation, without necessarily the baggage of subtyping. The fact that once you've committed to this interface with a supertype, now all the subtypes can be passed in willy-nilly as if they're an instance of a supertype. Okay? Other questions? Okay, so let's keep on going here.
I have a little question.
Yeah.
So, generally speaking, if you see that you're creating a subclass which might violate the Liskov substitution principle, you just create another class without extending it? Is that?
Yeah, you can perfectly do that. Yeah, sure. But the only thing is you won't be able to automatically reuse code that, like with course timer, right? Code that accepts course timer as a parameter or an argument that's of type course timer. You're not going to be able to pass any old class in as if it's a course timer. The only way is if it's a subtype. And that's it. I mean, subtyping and polymorphism provide great power, but they come with great responsibility. Responsibility to avoid breaking the code. We have to use them responsibly. And yes, we could create a new class, absolutely. And in fact, that new class could internally use a course timer if we wanted it to, but we can't pass around as if it's a course timer. Passing around as if it's a course timer implies it behaves in a way that is compatible with, that is consistent with a course timer. That's the property of polymorphism. Does this make sense? Okay, here's a puzzle. This is like a trip through memory lane. Quite a few of these I created for the final exams, and kind of wished at the time I think I featured them in class. So now I can feature them in class. Okay, so here we have a read-only inset on the left, and here we have two candidate subclasses. And the question is, do they adhere to the Liskov substitution or do they violate it? So the read-only inset, basically you create it from a collection of an array. You give it an array of headers, okay? And here you can test, is an int in it? And you can iterate through it. Great. Here's one candidate subclass. It extends read-only inset to provide for a size method. So you can ask about the size of that set. Is that adhere to Liskov substitution principle? problem with that. You're providing, again, extra observer functionality, just kind of observes the size. You're not doing anything that changes the behavior. You're not overriding a method. You're not doing something that changes the underlying class implementation, the underlying, you're not doing something that sets a value to it or something about the representation. No, you're just observing it. That's fine. Perfectly legit. Okay, class 2 here. Class 2, subclass is a read-only unset, but it has an insert method. There's a method to insert one. Allows you to insert things after it's created. Suppose someone only knows they have a read-only inset. Secretly, it's a derived inset. Could they be rudely surprised? How could they be rudely surprised?
It kind of implies that the set isn't going to change, but inserting would change the contents of the set.
Good. And in concrete terms, for example, so that's implied by the name. We live in a human theater, and names carry and communicate, are powerful ways of communicating intentions. But beyond that, there's also this is-in method, right? And we might think, if we had what we think is a read-only inset, we call is-in. We ask, after it's created, is 2 in the set? It says no. Then we might think reasonably that from there on, from that point later, 2 is not in the set. We don't have to check again, right? But secretly, if it was a derived inset 2, and someone could insert it somewhere else in the code, not in our code, we only know it's a read-only inset, but somewhere else in the code that knows it's a derived inset 2. Maybe it's in a method we call off to from our code or something. It actually calls insert on it and actually puts something else in it. Puts 2 in it. Now in our code, we count on the fact that once we check if 2's in it, we never have to check again, right? But now someone else has changed that, and we, our code breaks because we're assuming 2's not in there, and our code assumptions are violated. We say there's no way it could insert into the second element of the array based on the values in here, or the third element of the array, and it happened. So the issue here is that our assumptions have been violated because we built our assumptions around the fact once we check is in on a given integer, it's guaranteed to have that same value from now on. If it wasn't in it earlier, it's not going to be in it later. If it is in it early, it's going to be in it later. That, ladies and gentlemen, is a history property, right? The value of the read-only inset stays the same between any 2 points in time, and we violated that with insert. Okay. Comfortable with that idea? Okay. My read-only dictionary. Okay, this keeps track of dictionaries. This is a read-only dictionary. We have preconditions. Here we create a dictionary, strings and double elements. So strings are the keys, and the values are doubles. And basically, those 2 arrays have the same values, and there can be no duplicate keys. And here, basically, there's no keys that are null, and the size of the string is greater than 0. So I'm just reading this off. Incidentally, this is a type of specification that gets closer to what a compiler might understand in another 5 years or 10 years in terms of double checking things. Okay, so we have this. We create the dictionary once, and it has some properties involving its keys and its values. And then we can get an element. We could say, give me the value associated with a certain key, and we can ask, is a given key occupied? Is there an entry which has this certain value, this string, as its key? Okay, superclass, superclass. Here, this is a subclass, in other words, a subtype of it. Subtypes come along with subclassing. Subtyping comes along with subclassing, because in Java, anything that's a subclass you could pass around as if it's an instance of a superclass. Okay, so this is a public class my read insert dictionary. And that extends this one, gets all good reuse of that code, but it allows you to insert an element into the dictionary after the fact. Does this adhere to the Liskov substitution principle? No. No. For the same reason as the last one. Basically, someone could be counting on the fact they've tested once. Is this given key occupied? It got as one of my students used to say, a negatory answer. A negative answer. And so they think they never have to check again, but if it's secretly in my read insert dictionary, they could be really surprised. Now the value of it should change. Okay, here's another one. I know the horror continues. My read insert dictionary. This one extends my read only dictionary and allows for this insert. The issue is not whether this is a legitimate subtype. The question is this one to the right a legitimate subtype of this one? So the idea here is we have cat's out of the bag. We've got this class here with insert element in it, okay? And now there's another class that someone wants to create as a subtype of this one, a subclass of this one, that not only has this insert element, but as a set element. You can actually set the value associated with a given key. Insert element only allows you to insert a new one in. It only allows you to insert a new entry, whereas set element can allow you to change the value of an existing entry. Does that adhere to Liskov substitution principle? No, why not? Give me an instance where someone could be rudely surprised. I would note that the superclass does the ostensible the superclass does support get element, which allows you to get the element. So give me a case where someone could be rudely surprised.
Once you call a get element, you don't always expect it to return the same element.
Yeah, it's going to always have the same value from now on. You're counting on that. You never check it again in your loop. Checked it once, you figure that's enough because it can never change. And now it can change. So that's a bad thing. Okay? It violates this. Man, after this coverage, I'll be very confident you'll be able to perform well in these examples, in the final exam. So I would anticipate quite a few of them. Okay. So key points for reflections. These interface specifications are contracts. Okay. Interface specifications are contracts and must be adhered to by any implementation. Who relies on those contracts? Well, users of object instances of the class. So you have a C. You have a C. You say, new C, right? And here's your C. And you then call foo on it, and you call bar on it, right? You're using instances of it. This is what I mean by you allocated an instance called C of this class, and then we call things on it. So to do that, we reason about the interface, right? True or not? You reason about what foo does. What does it need? What are its preconditions, postconditions? True or not? Speak as in one voice. True, yes. Thank you. Another set of parties that might use it, these interfaces, these specifications, are creators of interfaces of subtypes. They need to. Because they have to be able to be used as if they were an instance of the supertype safely. So they need to reason about that interface as well. Deduce what could someone reasonably infer from that interface? What could someone reasonably conclude? And they have to adhere to those things, right? And as we'll see, there's also coupling for superclass creators. People who create superclasses, in fact, because if you subclass that superclass, you can override the methods of that superclass in ways that could be could lead to that superclass using your methods. So they have to be cognizant of this somewhat as well, and we're going to come to that next time. Okay, so providing specifications on these things provides people some way of deducing what is guaranteed and what's not guaranteed by a given class or interface. If you don't provide clear specifications, it worsens the problem. Either someone's not going to use your class, because this is too confusing, I don't know what's guaranteed, I'm out of here. I'm going to use some other class. I don't know if that's ever happened to you. I mean, I don't know, maybe in 371 or 370, you know, you have a choice between libraries, and one library seems better documented than another. And you end up saying, I'm not going to use that library. This library that maybe is underdocumented, it seems pretty good fit maybe, but you're just not sure what it does or what it guarantees. And so you end up saying, okay, I'll use this other library, which I don't like as much, but at least it's well documented, etc. This is a common thing, right? Not providing clear specifications can drive people away from our methods, from our abstractions. But it can also lead to people to make incorrect inferences, like based on the name of something, they conclude something, and that actually wasn't guaranteed. When we reason about a subtype interface, like we have to, we're not purely worrying about that subtype. We are purely worried about subtype interface. Not yet, not today, but yes, Tuesday, about its implementation. Okay, we're actually here in today's class, in the last two classes, including the video, we're reasoning about the promises made. The promises made by these classes, okay? And we're going to see there's a whole other layer of concerns that relate to our implementation of those promises. And there, ladies and gentlemen, there, the plot thickens. Because we have subclassing, which not only serves to introduce subtyping and all the responsibilities attendant to that, but it further introduces reuse of implementation. What do I mean by reuse of implementation? Why do I say that subclassing gives us reuse of implementation? Is that a hand up or no? No, okay. Definitely not. Okay. So what do I mean by subclassing? Like saying extends. How is that different than saying implements?
Implements only has specifications.
Good.
Not taking the code itself necessarily.
Exactly. Exactly the point. Andrew, you put it very well, and maybe I should have phrased it like that. Subclassing, if you say extends, you're doing more than just saying an instance of, so if you say D extends C, you're saying more than D can be passed around as a C. You're actually saying D gets, it inherits, is the term we use, all of the implementation of C that we don't override. Meaning all the fields, the instance fields in here, all of the methods of C, they get reused. They become part of D. We got the implementation of C now to D by subclassing it. Are you comfortable with that idea? We get that full implementation. And for many of us, that's a big draw to subclassing, right? We can build a top of C. That's one way we might talk about it, right? We build D on top of C. We get all its goodies, and then we can add more to them, right? It allows us to reuse the implementation of C. But it's more subtle than that, as it turns out. And one of the big subtleties is, ladies and gentlemen, if you say D extends C, it gets all its goodies, but then you override one of the methods that was originally defined in C, and that method is called from another method in C. So if you had, foo here inside of C, and it calls off to bar secretly, internally. Calls off to bar. And C also defines bar. And D, you subclass, and you override bar. You override it, right? You override it. Bar. Do you get foo also in D? By subclassing it? Yeah, you have foo. But who's foo going to call? Who's it going to call? Sorry?
Ghostbusters.
Thank you. I don't object to that answer, and I don't dispute it. But what method will it call? It'll call off to our bar. It'll call off to our bar. If you call foo on the subclass and you've overridden bar, and foo calls bar, and you call foo on the D, it's going to call D's bar. So now we've introduced this coupling that by reusing the implementation of C, we have to reason about how that implementation works to avoid breaking it. And that's going to be the subject of the next lecture. And it's going to lead to thinking about a new type of interface, which you will find in the Java docs associated with the Java library. You will find subclassing interfaces. These are interfaces that are not aimed at people who use instances, like C here, of that class. These are aimed at people who want to create a subclass, and they need extra information, like what method calls what method. Subclassing interfaces. And they will help us reuse, through subclassing, classes in a safer way. We still have to worry about all the Liskov substitution principle issues, which is about promises, not about implementation, but we also need to make sure the implementation is safe. And that will be the subject of our next lecture. Okay? After that, we will go on to discuss use of traits and mix-ins as alternatives to classic subclass. Traits as ways to sort of inherit from multiple things in a safe way, and mix-ins as a way to sort of separate reuse of code on the one hand, inheritance on the one hand, from polymorphism and subtyping. That's all for today. Thank you very, very much. I appreciate your tolerance of my soliloquies, and we will see you next time. Oh, before we meet again, I will be posting assignment 3. Okay. You'll be due the last day of class. I plan to post it over the weekend. Sort of refining and frobbing some elements or tweaking some elements of it. And we'll be releasing it over the weekend. Thank you.
Subclasses.
Yes.
When you add a new